So welcome back to National 4, National 5 Chemistry. The topic we're on is chemical formula, and what we'll be looking at today is chemical formula that contain Roman numerals and also chemicals that do not end in IDE. So the first part of this lesson is going to be for chemicals containing Roman numerals. So our aim is to understand how to write chemical formula for compounds containing transition metals, because these are the compounds where Roman numerals are used. So in terms of success criteria, we want you to be able to understand Roman numerals up to the number 8 and be able to write chemical formula for compounds that contain Roman numerals. So when it comes to transition metals don't always have the same valency. And they can transition from a valency of 1 up to a valency of 7. And Roman numerals are used in brackets after the name of a transition metal to tell you its valency. So for example, we have iron 2 chloride, manganese 4 oxide, and iron 3 hydride. In terms of our Roman numerals, this is what each Roman numeral means. So a capital I, sometimes written as a small I, means 1. 2 I's beside one another means 2. 3 I's means 3. That's quite straightforward. However, once we get to 4, the situation gets a bit more complicated. IV means 4. V means 5. VI means 6. VII means 7, and you can imagine VIII means 8. So you need to be able to remember those Roman numerals. It's most common for them to use the numbers 1 to 4 are the more common ones. Now, when it comes to working out a formula that contains Roman numerals, we can use the same method as before, the SVSDF method, but for the transition metal, we don't need to look up the periodic table to find out the valency. We can just take the valency directly from the Roman numerals in the formula. So we're going to work through an example here of iron 3 chloride. Now our symbols, the symbol for iron is Fe, the symbol for chlorine is Cl. The valency of iron we can tell because in Roman numerals we've got an III and that means 3. Chlorine is in group 7, and if you look at the periodic table, group 7 has a valency of 1. Now what we do is we swap these numbers over. So now underneath iron is a 1 and underneath chlorine is a 3. We ask ourselves, can we divide these to make anything smaller? And the answer is no. So we just write the numbers out again. And then we write the formula. So there's 1 iron and there's 3 chlorines. So that means FeCl3. And again, remember, if there is only one of an element, we don't need to write a number beside the symbol. Here's another example, copper 1 chloride. Well, copper has the symbol Cu, chlorine has the symbol Cl. Looking at the chemical formula there, it's copper 1 chloride, and so that means the valency of copper is 1. Chlorine is in group 7, so it has a valency of 1 as well. If we swap these numbers over, there's still 1 under each one. Can we divide them to make them smaller? Our answer in this case is no, so we write the numbers out again. And there is 1 copper and 1 chlorine, which means that the formula is CuCl. Got another worked example, nickel 2 oxide. Nickel has the formula Ni, oxygen, symbol O. From the chemical formula, it's nickel II, so that means a valency of 2 for nickel, and then for oxygen, it's in group 6, which means it has a valency of 2. We swap these two numbers over and ask ourselves, can we divide to make them smaller? And in this case, the answer is yes. We can divide each side by 2, and that gives us 1 and 1. So when it comes to writing the chemical formula, it would be NiO because there's one nickel and one oxygen. And one final example, manganese IV oxide. Symbol for manganese is Mn. Please do not confuse magnesium and manganese. Magnesium is Mg, but manganese is Mn, and oxygen is O. From the Roman numerals, we know that the valency for manganese is 4, and oxygen is in group 6, which means it has a valency of 2. When we swap these numbers over, we end up with a 2 underneath manganese and a 4 underneath oxygen. When we ask ourselves, can I divide these to make them smaller? You should hopefully be answering yes, because if you divide each side by 2, you end up with 1 underneath manganese and 2 underneath oxygen. Then we can write the chemical formula because we know that there is 1 manganese and 2 oxygens, so it is MnO2. So here are a few examples for you to have a go at. If you are able to do these questions, make sure you get yourself access to a periodic table and have a go. Pause it to have a go at those. If you're unable to access a data booklet or a periodic table at this stage, just skip on to the next part. If you have paused the video and are wanting to go over your answers, well, I can reveal that iron 2 fluoride should be FeF2, copper 2 oxide should be CuO, vanadium 5 oxide is V2O5, silver 1 phosphide should be Ag3P, and lead 2 sulfide is PbS, and finally cobalt 2 nitride is CO3N2. Next, what we're going to look at are compounds that contain more than 2 elements. And specifically, we're going to understand how to write chemical formula for compounds that end in ATE or ITE. In terms of success criteria for the second half of this lesson, you're going to be able to write chemical formula for compounds that contain more than 2 elements, use the data booklet to write chemical formula for compounds that end in ATE or ITE. Also, to be aware and use the data booklet to write chemical formula for compounds that contain ammonium or hydroxide in their name, and also be able to use brackets in chemical formula. So we're going to start off with hydroxide. Because in previous lessons, what we have said is that if a compound ends in the letters IDE, that meant that that compound only contained 2 elements. And you were told that hydroxide was an exception to that rule. Hydroxide itself is an ion made up from 2 elements, oxygen and hydrogen. The oxygen and hydrogen atoms in hydroxide are bonded, but they're bonded as a group and can still bond to other things. Hydroxide is an example of a complex ion, sometimes called a group ion, or sometimes called an ion made from more than 1 atom, which is the term ions made from more than 1 atom used in the data booklet. Now, a list of every single one of these ions made from more than 1 atom are found on page 8 of the data booklet. And if you read the names underneath the ion columns, you'll see that most of them end in the letters ATE, for example, carbonate, sulfate, nitrate. Some of them end in ITE, like sulfite and hydrogen sulfite. But there are 2 that don't use ATE or ITE. They are ammonium and hydroxide. Now, whenever we are putting these ions into chemical formula, what we do is we write the symbol in formula but ignore the charge. So for example, NH4 plus is written in the formula for ammonium, we would just write NH4. Now, in terms of working out the valency for these groups, well, if you look at the top column, sorry, it's top row, for each column, it'll tell you a number. So for ammonium, it's 1. For all those in the second, well, so in the third column, the ethanoate, hydrogen carbonate, hydroxide nitrate, it's also 1. For carbonate, sulfate, etc., the valency is 2, and for phosphate, the valency is 3. So all the information, the symbol, and the valency are found on that table on page 8. When we are using this, we're going to use exactly the same method as before, the SVSDF method. But remember, you're going to take the valency from the top of the column. The symbol is the formula in the table, but without the charge. So here is an example, sodium nitrate. It ends in the letters ATE, so we know that for the nitrate part, we have to look it up on page 8. The sodium part, we're just going to treat as normal, using whatever group sodium is in to work out what its valency is. So sodium has a symbol Na, nitrate has a symbol NO3. We know the valency of sodium is 1 because it is in group 1. We know the valency of nitrate is 1 because that's what's written at the top of the column where nitrate is written in that table on page 8. We swap them over as before, and we still have a 1 underneath each. We ask ourselves, can we divide them to make them smaller? The answer is no. So we have 1 Na and we have 1 NO3. So our formula is just NaNO3. Very straightforward. So our next example is calcium nitrate. It ends in ATE, so that means that nitrate we are going to have to look up in page 8 of the data booklet, but calcium we're going to use and treat as normal. So calcium symbol Ca, nitrate has the symbol NO3. The valency of calcium is 2 because it's in group 2. The valency of nitrate is 1 because it is in a column and that table in page 8 that starts with 1 at the top. When we swap the numbers over, we now have a 1 underneath calcium and a 2 underneath nitrate. We ask ourselves, can we divide to make these smaller? The answer is no. Now here we have got a new situation and a more complicated situation than we've had before, because we've got a number that is bigger than 1 underneath a symbol that has more than one element in it. And when that happens, we need to use brackets. So calcium, there's 1 of, so we write it as normal. In order to show that there are 2 nitrates, what we do in this situation is we put the NO3 in brackets and then we write the number 2. We only need to do this if the number underneath our symbol at the end, when we do our divide step, is bigger than 1. If it's bigger than 1, we put brackets around the symbol and then we put the number. So we have NO3 in brackets and then we have a 2. So if the number for a complicated ion is more than 1, we put the whole number and whole symbol in brackets, then a small number at the bottom right outside the brackets. Here we've got an example, ammonium sulfide. Ammonium is one of those 2 ions that doesn't end in ATE or ITE, that is still on the booklet on page 8. And sulfide means sulfur. The valency of ammonium is 1, the valency of sulfur is 2 because it's in group 6. When we swap the numbers, we now end up with a 2 underneath ammonium and a 1 underneath sulfide. So when we divide, can we make them smaller? The answer is no. Again, what we've got is a situation where we've got a symbol that contains more than one element, and we've got a number that's greater than 1 in the divide step. So what we are going to need to do is use brackets. So as we did before, we put the symbol NH4 inside brackets, and then we put the number 2 outside of it. And then we write sulfur. There's only 1 sulfur, so it's just an S. How we would read that formula is NH4 2s. Now we've got another example. This one is ammonium sulfite. Ammonium sulfite, both of these ions are on the data booklet on page 8. So ammonium is NH4, sulfite is SO3. The valency of ammonium is 1, the valency of sulfite is 2, and this is also taken from the table on page 8. When we swap them over, we now have a 2 underneath ammonium, we have a 1 underneath sulfite. We cannot divide to make them more simple, but we do have a situation where we have a number greater than 1 underneath a symbol that contains more than one element, so we're going to have to use brackets again. So we put NH4 in brackets, then we write the 2, and then we write SO3, sorry. Now, again, this is our final slide, so feel free to finish the video here if you want, or you could take the time to have a go at these questions and I will give the answers. So if you have had a go at those questions, the answers should be for aluminium nitrate, AlNO3, all in brackets, 3. For magnesium hydroxide, Mg, open brackets, OH, close brackets, 2. For ammonium chloride, NH4Cl, no brackets needed. For calcium phosphate, which is a complicated one, it's Ca3, open brackets, PO4, close brackets, 2. For gallium carbonate, that again is a complicated one. That is Ga2, open brackets, CO3, close brackets, 3. And then copper 2 sulfate is one which has Roman numerals in it as well. So remember that meant that copper had a valency of 2. So our formula is CuSO4. So that was us going through more complicated chemical formula using Roman numerals and then looking at compounds that contain more than one type of element and needing to use the data booklet for that. Our final lesson on chemical formula will look at ionic formula.